Hello all, welcome back to Methods of Operations research course. Until now we learned linear programming, integer programming and their solution algorithms. In today's lecture we will start learning goal programming, which is a useful tool to formulate some real-life problems and also to deal with problems which have multiple objectives. Until now, all formulations that we considered has a single objective, either to minimize the cost, minimize the time, minimize the distance, or maximize the customer satisfaction or something. But in some cases, we may have problems in which we want to minimize the cost and at the same time maximize the user satisfaction at the same time. Okay, so in these cases, how we can formulate? It's not possible to write two objectives at the same time in Cplex, for example, into the solvers. So we need a methodology to deal with such multi-objective formulations. And also, in some cases, instead of minimizing or maximizing an objective function, we may want to achieve a target level. Okay, we may want to satisfy the total distance of traveling not to be more than, let's say, 10,000 kilometers. The total cost not to be more than $10,000. Okay, or the user satisfaction level not to be less than 90%. So these values are our targets. They are goals we want to achieve. And in order to formulate such problems, instead of minimizing distance, cost, or maximizing user satisfaction, in order to satisfy these target levels, we may use the goal programming approach, which will help us satisfy our goals, our targets in the most suitable, most accurate way. Okay, so in this lecture we will start learning this approach through some examples. So let's get started. So as I said, in most of the optimization problems, we have only one objective, a single objective. We either try to maximize or minimize an objective function, subject to a series of constraints. But in most real-life problems, as I said, there may be more than one objective. For example, maximize the return or minimize the risk at the same time. Maximize profit and minimize pollution. So which one of these is the objective, real objective? We want to try to do both of them. We want to achieve both of them at the same time. Okay? And the thing is, the problem is, usually these objectives conflict with each other. So what does conflicting means? So if you want to maximize profit, for example, in a setting, that solution which maximizes the profit usually is not the solution which minimizes the pollution. Okay? So you cannot achieve both objectives at the same time. If you want to minimize something, then the other one will be worsened. So you need to sacrifice from the other one. Okay? So in this chapter, we are going to consider such problems and we will consider the goal programming approach. Until now, we said that there is this objective function of an optimization problem and there are the constraints. But the thing is, when we say these constraints, from now on, we will call them as hard constraints. The constraints that cannot be violated, okay, that might be satisfied. So if you write, for example, in Cplex, if you write an inequality as a constraint, then the model, the solver, must satisfy it. It cannot say that, okay, I couldn't satisfy it. I did my best and this is the solution. No, it must satisfy all of them. Okay, so these kind of constraints are called hard constraints. They must be satisfied. For example, there are 1,566 labor hours available. Then for your production plan, you need to satisfy this. You cannot exceed this available number of hours. Or your budget is 850, let's say, dollars. So you cannot exceed this. Okay, so it is a hard constraint for you. But in some cases, these hard constraints are too restrictive. It means that, for example, in this above example, you have $850, let's say, and you want to keep the project within that budget, less than this amount. But for some reason, if it's not possible to satisfy this, then you may exceed it a little bit. So there is this opportunity, there is this possibility. If that is the case, then we cannot say this as a hard constraint because you are allowed to exceed it. Okay, so for example, if you want to buy a car, you have a maximum price in your mind. Okay, so I want to buy a car approximately for this price, you say. Okay, so this is your goal, this is your target price. But for some reason, if you cannot buy the car for that price, if you cannot find it, so there is this opportunity for you, so you can find some more money and you can spend more. Okay, you can exceed that value. So these kind of restrictions are called soft constraints. Okay, these are target values or goals. That's why this approach is named as goal programming. So we want to achieve these target values as much as possible, but if we cannot, then we are allowed to exceed them as well. Okay, so in terms of the optimization problems that we learned until now, a hard constraint, the constraints that you must satisfy, are the regular constraints that we are writing. But the soft constraints, which means that we have a target value, but we are allowed to exceed it. But the thing is, we want to satisfy them as much as possible. So they are soft constraints. And in fact, these soft constraints are related to your objective functions. They are not really constraints. They are your objectives, your goals. So it is easy to explain the concepts with an example. Let's consider this example from your book. Okay, so in Fayetteville, which is a small city, so there are 20,000 residents in this city. The city council is in the process of developing an equitable city tax rate table. Okay, the annual taxation base for real estate property is $550 million. Okay, so in total, you can collect a tax all over from this value, and we will decide on what should be the tax rate, what percentage of this value should we collect as a tax. Okay. Also, the annual taxation basis for food and drugs. So this was for property, real estate property. Okay. The annual taxation basis for food and drugs and for general sales are $35 million and $55 million. So this is for food and drugs, and this is for general sales. Again, we will collect some percentage of this as a tax. Okay. On the other hand, annual local gasoline consumption is estimated at 7.5 million gallons. Okay, so this is the consumption of gasoline in terms of gallons. It's not dollars. Be careful, it's gallons. So the city council wants to develop the tax rates based on 4 main goals. Okay, this is the statement of the problem, but we have these following statements. Okay, it says that tax revenues must be at least $16 million to meet the city financial commitments. Okay, so we are going to collect tax from real estate property, some percentage of it. We will collect from food and drugs and general sales, and also from gasoline usage. And then the total amount should be at least $16 million. Okay, it says that food and drug taxes cannot exceed 10% of all the taxes collected. Okay, so this is food and drug, so we will take a percentage of that one as a tax, and that total amount of tax that we collect from this one cannot exceed 10% of the whole taxes that we collected. Similarly, general sales taxes cannot exceed 20% of all taxes collected, and gasoline tax cannot exceed 2 cents per gallon. Okay, so these are the requirements. Until now, without knowing this goal programming approach, what we would think is all these statements here are constraints. So we would write them as constraints. But again, we need to think, are they really constraints, or they are providing us some target values so that we should achieve? The problem may be this. Okay, we want to achieve all of these at the same time. But the thing is, when you write all of them as a hard constraint into the Cplex model, Cplex may return you an infeasible solution. It may tell you that, sorry, there is no solution to this problem. Then what would you say? Okay, sorry, there is no solution to this problem, so we will close up this city council, we will not collect any taxes. No, you should continue and find the solution, right? And that solution must satisfy these restrictions as much as possible. So how can we do this? The main problem that we are dealing is this. We want to achieve, if it's possible to achieve all of them at the same time, then that's fine, we want it. But if it is not possible, then we want to achieve them as much as possible. So these are our goals, our target levels. The first thing is to formulate this problem. Okay, so the problem is given here. Again, in formulation, we do as we did before. First thing is to define our decision variables. And what are we trying to decide on? Think about this. Okay, please try to do it by yourself by stopping the video at this moment. You should be able to write these restrictions, define your decision variable, and write these restrictions by your own, just as regular constraints, nothing different. Okay, try to do it, and then after that, please continue with the video. Okay, so we need to define our decision variables. The first thing is to define these decision variables. What we are trying to decide on. As we said, this is the total tax base for real estate property, right? So we will take a percentage of that one. And the thing is, we are trying to decide on what percentage of this should we collect as a tax. That percentage is our decision variable. So this XP is the rate, okay? The rate means the percentage of this value that we are collecting as a tax. Again, this 35 million for food and drugs, and we will collect a percentage of it, and we are trying to decide on it. So this XF is the proportion or the tax rate for food and drugs. and XS is the tax rate, similarly for the general sales. Okay, but for the gasoline we need to define it a little bit differently, because we are given this 7.5 million gallons usage of gasoline. Okay, so it is not the dollar values. So in this case we are not going to tell or define our decision variable as a percentage of this value, but we will define it as the tax, not the rate, but the tax itself in terms of cents per gallon. Okay, cents per gallon. Of course, you can define it as dollars per gallon as well, but dollar per gallon will be very small. So we define it as cents per gallon. So XP, XF, and XS are the tax rates that will be directly applied to these values, but XG is the cents per gallon, and it will be applied to this gasoline usage. Now let's try to write our constraints. The first constraint says that the total collected tax must be at least 16 million. Okay, so remember, for this real estate property, the total value was $550 million. So in every one of these we have these millions. We can just ignore the millions and use the remaining part. Okay, 550 is the base, tax base for real estate, and this XP is the rate, is the percentage of this that we are collecting as a tax. So 550 times XP gives me the total amount of tax that I am collecting from real estate. Okay, so similar to this, for XF and for XS, we also multiply them with their tax bases, so that this part over here is the total amount of tax that we are collecting from real estate, food and drugs, and general sales. On the other hand, for the gasoline, if you remember, the usage of gasoline, annual usage of gasoline was 7.5 million. Okay, and we defined XG as cents per gallon. So this is the total amount of gallons that are used in a year, and this XG is the cents of tax that we are collecting per gallon. But when we multiply these two, the total multiplication is dollars. Is cents. Okay, because this XG is defined as cents per gallons. Then we need to convert them to dollars, basically by just dividing this number by 100. Okay, when we do it, we convert it from cents to dollars, and then this value here, 7.5 divided by 100, gives you this number. Okay, so this times XG gives you the dollars that you collect from the gasoline. So this total summation here is the total amount that you collected as a tax, and we want this value to be greater than or equal to 16. Okay, so this is the first constraint. The second constraint, on the other hand, okay, says that the total amount of tax that you are collecting from food and drugs, what is it? The base for food and drugs was $35 million. And when you multiply this by XF, this is the amount of tax that you collected from food and drugs. Okay, it says that this value should be less than, okay, this value should be less than or equal to 10% of the total tax that you are collecting. So what is the total tax that we are collecting? In fact, that's this one here. This is the total amount of tax that we are collecting. And it says that this, for the tax for food and drugs, must be less than or equal to 10%. That's why we are multiplying it by 0.1. 10% of this total text. Okay, so this is the second constraint. The third constraint is very similar to this one, but this time it says that the total text that we are collecting from general sales, 55 times XS, must be less than or equal to 20% this time, 20% of the total amount of text that we are collecting. Okay, so these are the three constraints. The fourth constraint says that for gasoline, the text that we are collecting per gallon must be at most 2 cents. Okay, so this is 2 cents, and this xg, we defined it as the cents per gallon that we are collecting as a tax. So it means that xg should be less than or equal to 2. So this is the gasoline tax. And these four are the constraints given to us. Having these constraints, formulated these constraints, we can simplify them. So you see, for example, here we have xf here and xf here as well. We have 10% multiplied by this parenthesis. Let's get rid of them. Let's simplify them. So the first constraint, it's already simplified. The second one, just multiply this with the parenthesis and take this xf to the other side as well. Then what do we have? We have this constraint. Similarly, do the same thing for this one, and we have this constraint, and this is already simplified. So these are the simplified versions of these constraints. As I said, we want to achieve all of these at the same time. But sometimes achieving all of them at the same time is impossible. When you write all these as such constraints into Cplex, you may end up with an infeasible solution. In that case, we want to find a compromise solution among these conflicting goals. The goals are conflicting because it may be like this. If you want to satisfy this, then you cannot satisfy the first one because you want to keep the tax rate for the gasoline less than 2 cents. And since this amount is less than 2 cents, maybe it's impossible to reach this value. Okay, so they are conflicting. So, and our objective now, if we cannot we cannot satisfy all of them at the same time, we want to find a compromise solution. In that case, according to this goal programming approach, what do? We convert each of these inequalities into a flexible goal. We do not write them as constraints into our formulation, but we write them as goals, okay, as objective functions. Let me say. Okay, and with this method, the constraints are allowed to be violated if it is necessary. But the thing is, I want to keep this violation as minimum as possible. I don't want to violate any one of them, but if I need to, I want to do this in the minimum possible way. And in order to do this in goal programming approach, we use these so-called deviational variables. Okay, by using these deviational variables, we will reformulate the problem. How do we do it? It's very easy. For each constraint, we define two variables. Okay, so it doesn't matter whether the constraint was greater than or equal to, less than or equal to, or sometimes the constraints are equal to constraints. Okay, it doesn't matter. We define two deviational variables for each constraint. So remember, this first constraint was greater than or equal to 16. Okay, so for this constraint, we define this S1 minus and S1 plus, two constraints, and we converted the constraint into equality. Don't be confused. In linear programming, in order to convert a problem into standard form, we were including slack and access variables. Okay, if the constraint was less than or equal to, then we were adding a slack variable and changing this one to equality. If it is greater than or equal to, then we were subtracting an access variable and we were changing this to an equal to. But this is totally different. Okay, this is not the same thing. So don't be confused. These are not slack or access variables. For each constraint, again I'm repeating, whether they are greater than or equal to, less than or equal to, or equal to type constraint, for each one of them we define two variables. One of them is the so-called negative deviation. So that's why we represent it as a minus sign here. For example, S1 minus. It means this is the negative deviation from the target. And this is S1 plus. It is the positive deviation from the target. This 16 is our target, our goal. Okay. So by defining these S1 minus and S1 plus, they are variables. You see, they are here as variables. We convert this to an equality constraint. And we will, of course, talk about how these work. Similarly, for the second one, remember this second constraint was less than or equal to constraint. And for that less than, no, it was greater than or equal to, and we changed it again to equality by adding two new variables, S2 minus and S2 plus. So these minus and plus signs at the top, it doesn't mean anything. It just says that these are two different variables, first of all. And the second of all, it says that if it is a negative, this S2 negative, it means that this is a negative deviation from your target. So you could have defined like this. For example, this can be your A1 and this can be your A2. So instead of writing S2 minus and S2 plus, you could just write A1, A2, Y1, Y2. It doesn't make a change. Okay, it's the same thing. But if you keep it as S2 minus and S2 plus with these signs here, you will understand whether it is a negative deviation or a positive deviation. And while writing your objective function later on, it would be easier to understand which one you are penalizing. Okay, we do the same thing for all constraint. So this is the third constraint and this is the fourth constraint. We include these deviational variables. The thing with these deviational variables is this. So for each one we are including one pair of deviational constraints. So consider this first constraint, S1 minus and S1 plus. So they appear only in this constraint, nowhere else. And they appear, one of them with a plus sign and the other one with a minus sign. Because of these reasons, when you try to solve this using the simplex algorithm in the simplex tableau, both of these pairs cannot be basic at the same time. It means that in the optimal solution, either you will have S1 minus, this one will take a positive value, let's say it will be 5. If that's the case, then S1 plus will be 0. Okay, it will definitely be 0. So you will not have a solution in which, for example, S1 minus equals to, let's say, 5 and S1 plus equals to 7. Both of them positive at the same time. It's not possible. According to this, both of them should be greater than or equal to. So it means that they cannot take negative values. So they will not take positive values at the same time. Okay, this is an observation. Now let's have a closer look at the fourth constraint, which is this one. So by including these deviational variables, we converted that constraint into this form, right? So now assume that in our solution, this xg appeared to be 1, okay, in the optimal solution. Then in order to satisfy this constraint, since this S4 has a negative sign in front of it, and both of these variables should be greater than or equal to, the only way to satisfy this constraint is to have this S4 minus equal to 1, and this S4 plus will be equal to 0 in that case, so that the constraint is satisfied. Okay, so if xg value is 1, then S4 minus should be equal to 1. Okay, so what does it mean in real life? So when we come to this situation, when xg is equal to 1, 1 is less than or equal to 2, right? So what does it mean? We satisfied this constraint. So it means that we satisfied this goal. Okay, so it means that if the constraint is a less than or equal to constraint, and if the negative deviation null variable si negative is positive, like this one here, okay, then it means that the ith goal is satisfied. We didn't exceed our target. We reached our target. But on the other hand, let's consider the other case. Assume that this xg is 3. So 3 is not equal to 2, right? But still it's allowed. So we can exceed our target, but we want to exceed it in the minimum possible way. Okay, in order to satisfy this constraint when xg is 3, then it means that this negative deviation should be 0 and this positive deviation should be 1 so that you can reach. You cannot just say, okay, this is 3 and this S4 is minus 1, this negative deviation, because negative deviation cannot be negative. I mean, these deviational variables are greater than or equal to 0. They cannot take negative values. Okay, so the only way to satisfy the constraint is to have this positive deviation equal to minus 1. Then what does it mean if this positive deviation is greater than 0? What do we understand? We understand that our xg, our variable or our constraint is not satisfied. Okay, so if the constraint is less than or equal to, and if the positive deviation is greater than 0, then the goal is not satisfied. We understand it. Okay, so here what we try to do is we want to satisfy this constraint, and we understand that if this positive deviation is greater than 0, we don't satisfy it. If the negative deviation is greater than 0, it's satisfied. We want this case. We want this case to hold. We don't want this case. But if we are in this case, then we want it to be as minimum as possible. So therefore, our goal here, in fact, our objective here is to minimize, let's call it G4, the goal 4. We want to minimize the deviation from our target, and deviation only appears if this Si plus is positive. So G4 is equal to Si plus. We want to minimize the value of Si plus. Okay, this is very important. Please try to understand what we are doing here. If our constraint is less than or equal to type constraint, and if the negative deviation takes a positive value in the optimal solution, then the constraint is already satisfied. Then we are happy. But if the positive deviation takes a positive value, it means that we exceeded our target. So in this example, we exceeded our target by 1 unit. But the thing is, you can exceed it by 2 units, 3 units, 5 units. but our objective is to minimize that deviation as much as possible. That's why, as a goal, we want to minimize this SI plus. But this depends on the constraint type. Since the constraint type is less than or equal to type, we are minimizing SI plus. Then what happens if the constraint type is greater than or equal to? Let's consider that case as well. So at this point, please try to figure out what will be the result or the conclusion. So for the less than or equal to constraint, we try to minimize the positive deviation. And here, we should minimize the negative deviation. But let's try to understand the idea, the logic behind it. So let's consider this first constraint, which was a greater than or equal to constraint. And we converted that to an equality constraint by adding these deviational variables, negative deviation and positive deviation. Okay, so let's consider what happens in each case. Let's assume that this part, this total summation up to this point, appeared to be 14. Okay. Then in order to satisfy this as an equality to 16, we need to give values to these positive and negative deviations, and they are restricted to be greater than or equal to 0. It means that in order to satisfy it, we need to say that this S1 minus is plus 2 and the other one is 0, so that the summation is 16. Okay, then what happened? Our objective was to exceed this 16. So this part should be greater than or equal to 16. But in this case, it's 14. So we understand that whenever this negative deviation takes a positive value, whenever it is greater than 0, then in fact, we are not satisfying our target. We are not reaching our target. Then what do we want? What we want to do is to minimize this deviation. So if this is the first constraint and this is the first goal, so as the first goal, we want to minimize the value of this deviation, which is S1 negative. Okay. Let's consider the other case. Assume that this summation over here is 18. So in fact, we are exceeding our target value and we are happy. But in order to satisfy this constraint, what happens? Let's see. This plus S1 minus should be 0 and the other one should be 2, so that this is satisfied as an equality. Okay, so it means that whenever this positive deviation takes a positive value, whenever it is greater than 0, then we are happy, we satisfied the constraint and there's nothing to minimize here. But on the other hand, if this negative deviation was positive, then we couldn't reach our target and we want to minimize the deviation there. So the conclusion here is this. When the constraint is a greater than or equal to constraint, then our goal is to minimize the negative deviation. When the constraint was less than or equal to, we wanted to minimize the positive deviation. When it is greater than or equal to, we wanted to minimize the negative deviation. So, okay, then considering all of the constraints, what are our goals? The first one of the constraint is a greater than or equal to constraint. So therefore, we minimize the negative deviation. The second constraint is a greater than or equal to constraint. Again, we minimize the negative deviation. The third one is greater than or equal to, so again we minimize the negative deviation. The fourth one is a less than or equal to constraint, therefore we are minimizing the positive deviation. So these are our goals and we want to minimize their values. And our constraints now, these new constraints, new versions, okay? So we converted all of the constraints to equality constraints. And now we have 4 constraints. This is our formulation now. This is the goal programming formulation. But of course, we don't know how to solve this until now, because how can we deal with 4 different objectives? We will talk of it later on. But this is how we formulate it. Okay, so keep in your mind always for each constraint, whether it's less than or equal to, greater than or equal to, or equal to, we define 2 deviational variables. One represents the negative deviation, the other one represents the positive deviation. The negative deviation variable appears with a positive sign in the constraint. Positive deviation variable appears with a negative sign. This is very important. It doesn't matter whether it's less than or equal to, greater than or equal to. It's always the same. Okay? As I said, don't confuse with the slack and excess variables that we use to convert the constraints into standard form. This is something different. Okay? So when we do this, then we write for each constraint, we write one goal. Okay, that's why we have goal 1, goal 2, goal 3, goal 4. 4 goals for this example. And depending on whether the constraint is greater than or equal to or less than or equal to, we minimize either the negative deviational variable or a positive deviational variable. And this is the final goal programming formulation. In this example, we didn't have an equality type constraint. So in order to demonstrate how we proceed with these kind of constraints, I wanted to include one more constraint to the problem. Let's assume that we have such a constraint as well as the 5th constraint. Okay, this is the 5th constraint. So 550xp plus 55xs should be equal to 10. So what do we do in order to convert this to a goal programming approach? Again, you shouldn't say that, okay, this is already equal to, so I will keep it as it is. No, we are still adding new, negative, and positive deviational variables. Okay, we need to add and convert the constraint into this one. Whatever the constraint sign is, we need to do this. Okay, then what should I write as my goal? Let's consider each case and try to understand what happens. Let's assume that this part over here is 9 units. Okay, so it means that this part here is 9 units. In order to satisfy this as equality as 10, so it means that this negative deviational variable should be 1 and the positive deviation should be 0, so that the equality is satisfied. But what happened? If you look, this 9 is not equal to 10. Our goal, our target here is to have exactly equal to 10, but we couldn't achieve it. It means that we want to minimize this deviation. So we want to minimize as 5 this negative deviation. Okay, we want to minimize it. But let's see what happens when the positive deviation is also greater than 0. So now assume that this value here, let's say, is 12. Okay, again we cannot reach our target to be exactly equal to 10. So if this is 12 in the optimal solution, in order to satisfy this as an equality, this part should be -2 and this one should be 0. Okay, so it means that this as 5 plus is equal to 2. It is greater than 0. Okay, and it indicates that we couldn't reach the target. We deviated from that target and we want to minimize that deviation. So besides negative deviation, we also want to minimize the positive deviation as well. Okay, so for equality constraints, our goal is to minimize the sum of negative and positive deviations. In less than or equal to type constraints, we want to minimize the positive deviation. In greater than or equal to type,
we want to minimize the negative deviation. In equality type constraints, we want to minimize the sum of negative and positive deviations. Okay, so this is all we do to come up with the goal programming formulation.
Now it's time to test yourself, your learning. Reconsider the farewell text problem and assume that there is an additional goal, which is goal 5. And according to this goal, which requires that the gasoline tax to be equal to at least 10% of the total tax bill. Okay, now please try to write this goal by yourself. It will be a good exercise to test your learning.